All right, it looks like everyone is ready to go. Welcome. I'm so glad you were able to attend the web seminar this afternoon. My name is Bill Goebel. I've spent a lot of my career in new product development, so I have a lot of experience with hardware and software microcomputer design. I also spent a lot of time doing reliability and probability of failure analysis. So just a brief overview so you get a little background and you can understand a bit about where I'm coming from when I make certain comments. I work for a company called Exida. Exida is a global corporation with offices around the world. Exida is composed of a number of people who come from new product development groups, mechanical developers, software developers, and electronic hardware developers. Many of our people are former assessment agency personnel, so we have a strong certification agency background and experience. And many of our engineers are systems level engineers working for petrochemical, chemical, and nuclear companies. It's a nice group of people with a diverse set of backgrounds. It's very enjoyable arguing with each other, coming to some common conclusions, and I very much enjoy working here. Exida does a wide variety of services. We do consulting primarily at the systems level for both process safety and for cybersecurity of automation systems. We have a group who does product certification. We have done a lot of functional safety certification work per IEC 61508. We are also doing cybersecurity certification work per our accreditation from ASCII, the Automation Standards Compliance Institute. We do training, we have engineering tools, we publish reference materials, and Exida is responsible for and administers an individual professional certification program called CFSE, and there are different levels for functional safety and cybersecurity. If you are interested, the website cfse.org is listed below. It looks like a lot of different things, but there's one common thread between all these activities. They all have to do with automation systems, safety, and reliability. We spend a lot of our time in the process industries, petrochemical, chemical, and power. We also spend a good deal of time in automotive, especially in the last 5 years, and in nuclear. All areas where safety is very important, as well as reliability, of course. Exida does publish a lot of reference material when we develop new analysis techniques. We don't consider them company secret. We publish them in a book, and they're available from ISA or on the Exida website. I do see a comment. I cannot hear the audio, and everything seems to be correctly set on my PC. When I attend these seminars, I go up to the Voice and Video tab, and I click it, and there's a speaker button there. You got to make sure the speaker is not muted at that point. Of course, it also needs to be not muted and turned on down on your task control bar. Normally, I've found that if both of those places are clean, you should be able to hear the audio. I did want to point out that the latest book from Exida is a book on functional safety. It describes a product development process that meets IEC 61508 2010 version for SIL 3 capability requirements. And we're very proud of that book, and we publish it so that people can gain a practical understanding of this complicated standard. The book's available on Amazon.com or on exida.com. I do have a few housekeeping issues that I need to mention. Please mute your microphone so that we do not have any noise. Copies of all the slides used today will be posted and available for your download. There will be a recording of this presentation this afternoon, and everyone who has attended or signed up will get an email telling them how to get copies of the slides and how to replay the recording if they wish to cover a point again. There will be a survey where we will ask you, hey, how well did that instructor do anyway? And of course, you can give me very nice ratings. That's okay with me. If you have any questions, please don't hesitate to use the question and answer tab at the top of your screen. You can go up there and type in a question. I will read them and try to answer them verbally for everyone. All right, that was my checklist. Let's talk about IEC 61508. This is a standard whose parts were first released in 1998. So we've been living and working with this standard for over a decade. It applies to automatic protection systems, electronic, electrical, programmable electronic, including all mechanical parts that are used in any safety function. The standard covers both random hardware failures and systematic design failures. It is written so that it can be applied to a systems level or project level work. The standard calls this a bespoke system. For those of us in the United States, we call it a turnkey system, a complete custom system ready to go. It can also be applied for product level work and for what I call components even, like microprocessors and even operating systems. There are two fundamental concepts in IEC 61508. A concept called the safety life cycle, which is a detailed engineering process. The primary reason for this is software reliability, and the concept is reduce the number of design mistakes. Notice I didn't say eliminate them. Nobody assumes perfection. But what we must try to do is create an engineering process that avoids mistakes and other steps to catch and correct mistakes. They're called systematic faults in the standard. The other concept, which was quite controversial when the standard was first written, was the concept of a probabilistic performance-based system design. In other words, there are no prescriptive rules on exactly what kind of redundancy you need and exactly how you're going to do your design and what kind of parts to use. Instead, you, as a system designer, must evaluate the expected probabilistic performance. Now, that is meant to reduce the number of random failures to an acceptable level. These two concepts have been in since the beginning, and they are still there. They have served us well for over a decade, and we expect them to continue to work well. Overall, when I look at the new version of 61508, I am quite pleased with it because a large number of items have been clarified. I view them as clarifications, not really fundamental changes. And of course, there were many interpretations of the standard, and many people who made interpretations like Exida and other certification bodies submitted our interpretations to members of the Standards Committee And I'm pleased that most of these were added to the standard, which is a good thing. One fundamental thing that changed in 6158-2010 is the concept of a new term called element. And you can read the definition, part of a subsystem. Now, it still can be confusing, but in fact, what they're talking about now is a product, a part like a solenoid valve or a pressure transmitter. And the term can even be used to mean an integrated circuit, a particular analog to digital converter, or a microprocessor, or an operating system. The clarification is important because there were some who argued that 61508 could not be applied to such what are now called elements. But in fact, that's one of the primary applications of 61508. And we don't need overall safety functions. Those are things that are defined for the system level. Element safety functions are now the requirements for specific products. And this clarification was very important because, in fact, IEC 61508 is frequently used for product certification. Keeping in mind that functional safety means that a device operates correctly in response to its inputs or fails in a predictable manner. And by the way, that second phrase, fails in a predictable manner, that's the difference between reliability and safety. In reliability, we don't care how it fails. We care if it works or if it fails. But in safety, we care how it fails. So I always considered safety to be a subset of reliability engineering. Functional safety certification is absolutely being done per IEC 61508 ever since it was actually, before it was first released. And the result is typically a certification and a certificate and a certification report. The advantage of certification is that a manufacturer has demonstrated design quality. The end result is a certificate indicating the SIL level for which a product is qualified and the standards that were used. Basically, it's a representation of high design quality. There's been a strong trend toward IEC 61508 certified products. It started in the process industries, and now it's moving rapidly to machine industries, to nuclear, and even to components like operating systems and microprocessors. Exida does maintain a list of certified equipment for the process industries. It's on the website, link is here. Take a look at it. I think you'll find it quite interesting if you've not really have an idea of how many products have actually been certified. SAEL-online.com. Now, there are major changes in 2010, and I've categorized them according to 8 particular items. Number 1, there are changes in functional safety management. Number 2, there are changes in the definition of low and high demand. I'll explain what that is. Number 3, there are some strong and powerful changes in requirements for traceability. Number 4, there are good, strong changes in the concepts and clarifications for how to use the concept of proven in use. There are changes in systematic capability. There are changes in the hardware design. 3 are major in my mind. The change in this metric called safe failure fraction, SFF. There's a new requirement for, really, it's electromagnetic compatibility, CE susceptibility. And many consider the change for application-specific integrated circuits as a real big deal. In the world of software design, there's good changes in criticality regarding tool evaluation. There are changes and strengthening requirements for code coverage and complexity management. And lastly, there is a requirement now for cyber security evaluation, which we're going to talk about. Let's take a look at the functional safety management changes first. In the new version of 61508, it is clearly recognized that a product can be considered a compliant item, and there's a requirement now specifically stated that a compliant item must have a safety manual. Now, I'm not sure many people consider this a big change. This requirement was assumed or interpreted by many certification agencies based on the operations and maintenance requirements of the standard. However, some certification agencies in the past did not require a manufacturer to create a safety manual, and now it is explicitly required. There is now a checklist of all the items that belong in a safety manual. And if you look at this list, you should realize that this is a list of all the things that a systems level designer should know. What's the end purpose then of the safety manual? It's to tell the customers of any particular product or element, I guess we should call it, exactly what they need to know to design a safe system. Now, that's a good idea. This is real common sense stuff, just like most of IEC 61508. Now, there is a functional safety management. Another requirement is personnel competency. There was always a statement that said you should use competent people, in effect. But now it's been clarified to say that when you judge competency, you must consider the responsibilities of a person and the level of supervision required for each role in a project. Okay, think about that for a minute. Responsibilities and level of supervision for each role in a project. Now, to me, that makes perfect sense as well. What we have done at Exida, for example, is we have defined all the tasks that we normally do as part of a project, a systems level project or a certification project. Whatever type of project we're working on, we have a list of all the tasks. And for each task, we put down the requirements. In this case, for example, if we send an engineer to help facilitate a software criticality and HAZOP analysis, we have two categories, junior and senior. For the senior level, a CFSE personnel certification is required. And we have 4 primary education and experience requirements. They must hold an undergraduate degree in engineering and have 3.5 years of experience, plus 1.5 years experience in the certification of functional safety products with software content. They must have read 61508. They must have in-depth knowledge of software criticality. They must, you can read the rest of these. Now, there's 4 primary activities. Now, for each, here's what we have done. For each person who is authorized to do software criticality analysis, we must evaluate and document that they meet these 5 primary criteria. And I don't know if you're like me, but when I first read this, I thought, oh no, what a bunch of busy work. But I had to do it anyway. So we sat down, defined the tasks, defined the requirements, and started evaluating all of our people. And I'll tell you, it wasn't nearly as bad as I thought it would be. It only took me 2 days, some debates back and forth. And when we got all done, we recognized that we had some very specific training and personnel development needs. And we put together an action plan. And although it did take a couple days, it was well worth the effort. I concluded when it was all done, boy, this was a good thing to have done. And of course, I'm happy because when the ANSI accreditation audit occurred, they went through all these records, and they thought it was, we passed with flying colors. That was well done. And in addition, for functional safety management, the 2010 version of 61508 has some annexes called properties. And properties like completeness, correctness, and consistency are defined. Now, oh boy, you look at this and you think, these are very abstract terms. I mean, how do you demonstrate completeness, correctness, consistency? What you need to understand, however, is that these properties were put into the standard to help people justify alternative measures to meet the standard. What if there's some new programming construct or some new programming language that isn't specifically mentioned in the 2010 version of the standard? What if a very clever computer engineer comes up with a whole new way to validate software correctness? Well, that new way will not be listed in the standard and may not be listed for years. However, it may be used if you justify it via showing that it meets the required properties. So I'm pleased that the standard gives us this kind of flexibility. In my opinion, that's one of the great strengths of this standard, that it allows alternative means to achieve product certification. The second thing that changed, the second big thing that changed in my mind, is the definition of low-high demand. In the original version of 61508, there were 3 demand modes defined: continuous, high, and low. Now that's important because when doing probabilistic analysis, there's 2 fundamental concepts: low demand and high/continuous. If you have a low demand application, you do probabilistic analysis based on a table called the PFD average table. You can absolutely take credit for manual proof testing in your design, and you can absolutely take credit for any automatic diagnostics, because those are things that reduce the probability of failure on demand. And once you understand these concepts, it's totally logical that proof testing and automatic diagnostics would improve safety. If, however, the dangerous condition, which is called a demand is a dangerous condition. If the demand occurs frequently, like let's say every hour, and you do a proof test once a month, that's not going to do you much good, because you've already had many dangerous conditions before you discover that your unit is not working properly. So in high demand and continuous demand, there's absolutely no credit for proof testing. Now, you might be able to take credit for the automatic diagnostics depending on how often the dangerous condition occurs. So a little background on definitions of these modes. Now, in the 2000 version of 61508, the definition for low demand mode basically said the demand occurs no greater, the frequency of demands occur no greater than once per year and no greater than twice the proof test frequency. Now, when I first read that, I was thinking, now remember, I understand the math behind this. And the proof test frequency has everything to do with whether you can use PFD average or not. And no greater than 1 per year has nothing to do with whether you use one table or the other. And so other parts of the standard even contradicted the definition in Part 4. And so, in general, Exida wrote up a definition that basically said low demand mode. We got rid of the once per year thing because it's only an example. This made perfect sense to me. Unfortunately, the new version of 61508, I did turn in a comment, please get rid of the once per year, but instead they got rid of the proof test frequency. I think someone just misread my comment, perhaps. But that's what the standard says right now, so we're going to have to live with it. Fortunately, it only affects system design. And I think it's very justifiable to use mathematically correct techniques, even if they violate the definition in the standard. But so far, nobody has challenged that. But right now, the definition for low to high demand has changed, and in my opinion, not for the better. But that's the only thing I don't like about the new version. Traceability, the third major category. Traceability requirements have really changed. They were strongly modified. Traceability was mentioned, but not specifically. Now, very specific traceability is required between different design levels. I see another question. Good question. Thank you, Tom. What does PFH stand for? Probability of failure per hour. And it's effectively equivalent to a failure rate calibrated on a 1-hour basis. It's a concept that applies to high demand and continuous demand applications. Thanks for asking. Back to traceability. Look at these different levels. You must trace between requirements, between safety needs and requirements, between the architecture design, between specific design specifications, integration tests, module tests. Those of you who are software developers are looking at this, I bet you, and saying, oh my goodness. Yeah, a lot of people are saying that. It helps, but remember why this is done. It helps to ensure completeness. It helps to ensure that your testing at all levels of design is thorough and complete. Why is that important? The testing helps you detect design mistakes. And we're trying to achieve a high level of systematic integrity. But whether you agree or not, there is a strong requirement for full traceability. That is also documented. Now, it does vary somewhat between different SIL levels. This is an example chart which shows some of the traceability lines. And you can see that for SIL 1 and SIL 2, it's required. Recommended, I guess is the word, sorry. And for SIL 3 and SIL 4, it's highly recommended. Now, what does that mean? Basically means that for SIL 3 and SIL 4, you absolutely must do it and no excuse will be accepted. For SIL 1 and SIL 2, it means you really better do it unless you have a really good justification. That's the difference. Traceability requirements are strengthened. The proven in use concept has been strongly clarified. In fact, in the 2000 version, proven in use was a concept that was used to demonstrate systematic integrity, but it was only mentioned in Part 2 of the standard, which covers hardware, and there was an open question about whether it covered software. Many certification agencies interpreted the statements as covering the system, which include hardware and software. But not everyone did. And the 2010 version clears this up by clearly stating in Part 3 that software is covered by the proven in use concept. In fact, you can typically use a combination of design process and proven in use. If it's a brand new product, of course, your design process, your safety life cycle, must meet the requirements of the standard. But if a pre-existing software is available, and that is the term they use in Part 3, pre-existing, then you can analyze the process that was used to develop that software, and you might consider the successful operational hours in the field. And if you have a sufficient combination, you can justify certifying that pre-existing software. Now, there's a new term for this, which I'm very pleased about, because previously the term safety integrity level was actually used 3 different ways. It was used to describe the risk reduction requirements determined by a professional risk analyst. People at the systems level who are doing hazards and operations studies will often identify potential problems, and based on tolerable risk criteria will assign a risk reduction factor. And you can see the SIL level is order of magnitude risk reduction. But it implies, it refers to a target, something to be achieved by a safety function design. It was also used to indicate the probabilistic failure on demand or probabilistic failure per hour for high demand, continuous demand systems. It was also used to show the evaluation of your probability of failure. Thirdly, it was used to determine the engineering process. And you know, I never realized this term SIL was being used in 3 different ways until I saw IEC 61513, the nuclear industry specific standard, and they used 3 different terms for these 3 things. And that's when I realized, boy, they've done a better job. So I'm real pleased to say that 61508 has at least created a new term for number 3, systematic capability, or sometimes called SIL capability. Now, this is an important concept because SIL capability refers to the level of engineering rigor. For example, remember that chart I just showed you on traceability? There were 2 particular lines that showed you that the traceability was recommended for SIL 1 and SIL 2, but it's highly recommended for SIL 3 and SIL 4. So that's an example of the engineering process rigor that changes as a function of SIL level. Now, if you meet all the requirements for the engineering process at a given SIL level, that gives you a SIL capability. Now, it's important at the systems level design because if you have a product that has SIL 2 capability, you cannot use it in a SIL 3 safety function, no matter how many of them you put in a redundant architecture. So you understand, this is a really big deal for systems level design. Now, why? Because if you put in 2 identical pressure transmitters in a redundant design and you calculate the probability now meets SIL 3, probability of failure goes from SIL 2 to SIL 3 because of the redundancy, that's neat. That's great. However, you're ignoring the concept and the reality of what is called common cause failures. Design defects often result in multiple failures of a redundant system. Did you hear that? Multiple failures of a redundant system. In a redundant system, you think the system will never fail because you have all this redundancy. But in fact, redundant systems do fail. I've experienced some of that personally, and I'm sure many of you have. You know what I'm talking about. That's why the design integrity, the systematic capability is so important. If you have a SIL 1 rated product, it cannot be used in a SIL 2 or a SIL 3. A question came up. Isn't this impractical? Yeah, what if you buy, oh, this is excellent. What if you buy SIL 1 sensors from 2 different vendors? That's a good question. The standard does not specifically get to this level of detail. However, there is a word that indicates that, notice I used, when I talked about common cause, I did talk about 2 identical. So the question is, what if we buy SIL 1 sensors from 2 different vendors? You have definitely reduced the probability of a common cause failure. In the end, you will have to judge whether that is sufficient because as the system designer, you are responsible. But in fact, if you have what is called a diverse sensors, you can probably justify moving up 1 SIL level. And I think there is a statement. I just can't remember where it is right now. There is a statement to that effect. So that's a good question. Thank you. Doesn't change the fact that SIL capability is a measure of design quality. And I would think you'd want high design quality. We used to call that SIL level, and now it's called SIL capability. There are more clarifications in 61508, and there are 3 different ways to achieve SIL capability: Route 1, Route 2, and Route 3. And this is also good. Now another question came up. Doesn't redundancy reduce the likelihood of a random fault? Well, it depends what you mean by that question. Redundancy absolutely reduces the probability of system failure if the redundancy is designed to tolerate that failure at the systems level. So in effect, yes, is the simple answer to your question. Now, it doesn't reduce the overall random failure rate of any particular element, but it absolutely is capable of reducing the random failure rate at the systems level. I mean, that is the whole idea behind it, and it is valuable. Redundancy is a valuable concept, which people discovered decades ago and are still using to great advantage. However, if failures are not independent, and if in fact there is a probability of a common cause failure, it doesn't reduce the likelihood of a random fault to as much as it might. But if you want to study that in great detail, I've definitely got several books to recommend. Whoa, the software, well, there's a lot of changes, and some of the changes are hardware design. No fundamental changes. Most everything is the same as it was, and most hardware design processes and tools today meet the requirements of the standard. However, the definition of fail-safe has changed. It's number 1. Number 2, the ASIC design process is now required in a manner similar to software. And number 3, there is now a reference to another standard for electromagnetic interference and susceptibility. Now, let's take a look at this first change, the definition of fail-safe. In the 2000 version of 61508, we had real clear, complementary, and I mean that in a mathematical sense, mutually exclusive and complementary definitions for fail danger and fail safe, because fail danger had a clear definition of failure that prevents the safety function from working, and fail safe was anything else. Anything else. And that makes perfect sense. They are complementary definitions. However, the problem with that definition of fail-safe is that most practitioners think fail-safe means a false trip, and this definition was not of that type. I do see another question. Let me deal with that later. The question says, will new clarifications result in recertification for systems installed base, systems under development? We definitely should talk about that at the end. So thank you for asking, Benjamin. But I think if I explain some other things first, I can answer this question clearly. Now, what happened in the 2010 version of the standard to the definition of fail-safe? Well, it became the practical definition normally used by practitioners. Fail-safe means a failure that causes a false trip in a single-channel architecture, by the way. Now, that means fail-safe and fail-danger are no longer complementary. They're still mutually exclusive, but not complementary. One of the new failure modes is called no effect, a failure of a component in the safety function which does not cause a false trip or prevents the safety function. And you'd be thinking, now come on, how can you have that? Well, what if you had components that did nothing but automatic diagnostics? If they fail, you will lose your automatic diagnostic capability, but it won't prevent the safety function from working, nor will it cause a false trip. In reality, there are such things. Interesting. So the standard is really improved in terms of realistically classifying failure modes. I'd like to say, hey, we've learned a lot in the last decade. The formula for safe failure fraction has not changed, but the results change because the definition of safe changed. And you know what this safe failure fraction is all about. Well, there are two types of products, type A and type B. A is simple stuff, you know, like resistors, transistors, springs, O-rings. And B is basically microcomputer stuff. That's the simple explanation. A is simple devices, B is microcomputer stuff. And there are tables in 61508 limiting the SIL levels for type A devices as a function of the safe failure fraction. So this is also a constraint on design. And it gets an order of magnitude worse when you go from type A to type B. You can see that by comparing those two charts. Therefore, the safe failure fraction metric is important. It's an important variable for those who are getting a product certified. If you want a SIL 2 capable, well, if you want a product that'll meet SIL 2 and you don't have a good enough safe failure fraction, let's say it's a smart pressure transmitter, you want to meet SIL 2 with a hardware fault tolerance of 0, you must have a safe failure fraction greater than 90%. That means you have to have a certain amount of diagnostics or a design that's inherently fail-safe or something that's good. And this table has been quite useful. It's just a little harder to meet now, that's all. The second change, or the next change, I see we got a question. Isn't that hard to meet? Good question. Is it harder to meet the safe failure fraction table now? Answers, yes, it's harder. Is it that much harder? No. Because most of the diagnostics and most of the no-effect failures are typically a very low number. And I can tell you that I have done analysis on about 200 different components, and all the smart components, none of them that previously passed now fail. In one case, a manufacturer had chose to add some more diagnostics to improve the safe failure fraction, but that's a good thing, and I'm glad he did it. It makes the world safer, so it's not that hard to meet, but thanks for asking. The second big change in the world of software, and this is a big change to some people, were design process requirements for ASICs. Now, I'm talking about field programmable gate arrays, programmable logic devices, and RAM-based programmable logic devices. All of these are now considered ASICs, and a rigorous development process is now specified. There are requirements for 4 different phases of typical custom ASIC design: design entry, synthesis, placement, routing and layout, generation, and finally chip production. Design entry are the requirements that most element or product designers must meet. And you must use a hardware design language. You must justify your tools. You must create a modular design. You must test your design. Test coverage must exceed 95%, and you must have code inspections or walkthroughs. Now, some people read this, and it was quite controversial when it was first proposed. I remember sitting in an airport arguing with a guy, and this guy was telling me how horrible it was that this was added to IEC 61508. On the other hand, I remember giving a seminar to some designers at a transmitter manufacturer. And when we got all done, I said, well, what do you think of this? And the answer was, why would anyone do it any other way? Those who were involved in quality design would have been using all these techniques. And, as he said, why would anybody do it any other way? You don't want mistakes in your ASICs, even in your field programmable logic devices. Now, some of the other requirements are also important: simulation, timing, checking of gate net lists, but some of these requirements are only applicable to single layer and multi-layer custom ASICs. And so for field programmable devices or RAM-based programmable logic, the applicable standards are applied. The other standards are simply marked not applicable. For example, placement, routing, and layout generation. You don't do any of that for a field programmable device. You do this for custom ASICs, even if it's single layer. And of course, chip production designs need a good quality system, but this is nothing that the semiconductor manufacturers haven't been doing for decades. One thing that is happening now is semiconductor manufacturers are getting their components IEC 61508 certified. Interesting, isn't it? The bottom line is you can't do anything you want anymore. You must use good engineering process. Not a bad idea in my mind. What else? In hardware design, there is now a reference to another standard, IEC 61326-3-1. And that standard is entitled Immunity Requirements for Safety-Related Systems, etc. This standard has higher test limits and more rigorous test criteria than the previous standards used. And so it's going to be a little harder to meet. On the other hand, some of the test criteria previously allowed a potentially dangerous failure while the electromagnetic radiation was applied, and it was still called a pass. And that just never made any sense to me. And they've corrected that, or I should say they've clarified that. Those of you who have designed hardware and tried to meet the European Union electromagnetic interference requirements probably agree with me in that it is an art as much as a science. Certainly no one ever taught me how to do it up front. It's not like Ohm's law. I can calculate the resistance and the current. Nobody ever taught me how to calculate the magnitude of electromagnetic radiation. It depends on the layout. It depends on the packaging. It depends on the frequencies. So, as a practical matter, most people just build it and test it. That's when you get out the copper tape and figure out what you have to do to change it. So it's going to be harder now, is the bottom line. But there's one really nice thing that happened. This 613263-2 excludes proven in use products from this requirement, and so we do not have to go back and redesign all the equipment that's been working very nicely in the field. Thank goodness for that. Now that's the hardware design requirements. What about software? 3 fundamental changes or clarifications. Tool justification requirements are now clarified. Code coverage test analysis is very clear now and strengthened, and code complexity is now required. Code complexity control is now required. What do I mean by this? 61508 has always had requirements for tool justification. This says basically, and the concept is very simple and common sense. Anybody that uses a tool must understand how it works. Oh, I have a terrible tale to tell you. In the final assessment audit from a 61508 certification project, the assessor asked to witness the RAM test. The instrument had previously passed during module testing, during integration testing, and this was the validation test. It failed. A bad bit was inserted into memory via an emulator, and the RAM test did not detect the bad bit failure. All of a sudden, there's lots of activity. Everybody's running around. What happened? Look what happened. You just failed your assessment audit. Do you know what that means in terms of project schedule and cost? It's horrendous. Months and months of delay, hundreds of thousands of dollars of expense, because they have to go through a whole new development cycle. You know what happened? During final integration testing, they discovered that the CPU communications routines weren't running fast enough. So they increased the optimization level in the compiler. It solved the problem. Now the communications routines worked with plenty of time to spare. They finished integrating the product, did the validation test, and released to assessment. The optimizer, being a smart program, noticed that the RAM test did nothing but store something to memory, read it back, and check to see if it was the same. And the optimizer said, ha, we don't need this code anymore, and it eliminated it. The poor guy who was doing the development, the build, didn't know how the tool worked and caused a 61508 assessment failure. Now, so you understand the concept. If you use a tool, you got to know how it works. common sense. But it wasn't clear how much evaluation you had to do, how much documentation you had to do. So now it's much clearer. There's a statement that said online support tools that can directly influence the safety system must be considered safety related. There were some who argued that online support tools were not safety related and therefore did not have to be part of the certification. Offline support tools are now in 3 categories: T1, T2, and T3. And you can read the differences. Basically, T3 is something which might, directly or indirectly, cause a fail danger. T2 is a situation where errors in the tool might prevent you from discovering a problem, but it basically takes a problem in the tool and a problem in the code to impact the safety-related system. And T1 generates no outputs which can impact. That makes it very clear, and the level of justification is very different for T3 versus T2 versus T1. And you can read exactly what these differences are. The main concept that I want you to get is that you don't have to spend all your time, a lot of time, justifying T1 anymore. And that's really good news. Whoops. Code test coverage is now specified, and it's a function of SIL level. Previously, code test coverage was only required for SIL 3. Now there are different levels of code test coverage required for SIL 1, SIL 2, and SIL 3. Code complexity control is now required, and of course, many of you software engineers know that complexity can be measured, and there are requirements for measuring the complexity of each module, and some determination made as to exactly what kind of complexity levels are allowed. Most companies choose a McCabe complexity metric of 10 as the upper limit, but that's not specified in the standard. Cybersecurity is now mentioned. Of course, cybersecurity was not referenced at all in the 2000 version of 61508. I mean, why would anyone think about cybersecurity for industrial control systems? Who would want to hack into an industrial control system? And then came Stuxnet. Nasty. Stuxnet has been thoroughly reverse engineered, and all the details are now posted in the hackers toolkit. This is not good. What 61508 now says is malevolent and unauthorized actions must be addressed during hazard and risk analysis. If a security threat is reasonably foreseeable, yeah, it is now because of Stuxnet, then security threats analysis should be carried out, and a vulnerability analysis shall be undertaken in order to specify security requirements. The bottom line is figure out what can go bad and do something to make sure it won't fail danger. It's kind of a big deal. I see another question's come up, but I'm going to answer it right at the end. Now, what do we do with this? How do we deal with it? Well, certainly it's not specific. So, in general, people are looking for specific requirements, and fortunately for us, the ISA Security Compliance Institute has released a set of specified requirements for embedded products security. Now, that is not yet a standard, but it is passed by a group of end users and manufacturers. Chevron, ExxonMobil, Siemens, Yokogawa, and a number of vendors and end users have released these requirements. They've gone through the ISA process. And in my opinion, the ISA Security Compliance Institute requirements represent an excellent way to show compliance to that statement of 61508. There are 3 levels: network robustness testing, a functional security assessment, which includes a threat and a vulnerability analysis, as specifically mentioned, and the development lifecycle assessment, which involves the design process. And those of you who are experts in control system cybersecurity understand that you'll never really achieve secure systems unless they're properly designed in from the beginning. And so the upper levels, of course, apply mainly to new product development. The IEC standards requirements have been submitted to the ISA SP99 committee, and they are expected to become a standard soon. In the meantime, they are excellent ways of demonstrating 61508 compliance. Now, let me deal with a couple questions. 1. What is considered an online support tool? Okay, let me think. Online support tool. A couple examples come to mind. In the world of process industry automation, I have seen systems that connect a HART multiplexer through an asset management software package, and it's online, operating. Now, I know not everybody keeps these online, but if you kept that online, monitoring all the time, that would be an online support tool. Now, could that tool fail in some way that would impact the safety function? Well, what if there was some combination of code that would inadvertently change the range on a pressure or temperature transmitter without changing the corresponding set point in the logic solver? That could absolutely be a fail danger. Therefore, all such software packages and hardware packages are now considered safety related and need to be part of the certification, or must not be used except for commissioning and maintenance. I hope that example is helpful. I can think of some others, but they're of the same type. Now, there's a question: Will these new clarifications result in recertification requirement for systems proven in use, installed base, systems under development? Bottom line is, it depends on the country you're in and the specific regulations by which you operate. Generally speaking, there are some fundamental rules. Systems, I don't know of any regulatory requirements for updating existing systems that are in the field and installed. I don't really know of any regulatory requirements for systems under development. I do know of some regulatory requirements in some countries where brand new systems require products that have been certified for 2010. Now, in my mind, it's still a little early for that, but I will tell you that many manufacturers are getting their products recertified per the new version of the standard. In another year, I think a majority of certified products on the market will be certified per the new standard. But that doesn't, common sense would not require recertification of the installed base. But that depends on the regulatory environment in each country. Good questions. Thank you. If there are more, please type them in. In summary, in my opinion, the new version of 61508 has done a great job clarifying many of the common interpretations being used primarily by certification bodies. There are absolutely stronger requirements in many areas, and these should result in better designs and fewer design mistakes. Although some people consider the requirements quite onerous and painful, as our expert said, why would you do it any other way? You don't want field failures. Lastly, it will be harder for a product manufacturer to get certified, but not too much harder. It's not that bad. Mostly it's just clarification. So don't be scared of it all. Embrace it and think of it as good, common sense engineering techniques. Well, I want to thank all of you, and I hope you felt your time was well spent. As I said, you will be able to go through this again. You will be able to download copies of the presentation, listen to a recording of this session. And I will say that if any of you have questions that pop up later on, you may send me an email. I'm typing in my email address. Now, don't pass this out to the spammers, please. But if you have a question, don't hesitate to ask. And I will try to get back with you in a reasonable amount of time. I appreciate your attention, and I hope you've learned something useful. If you have any other questions, send me an email. Thank you all very much, and I hope to hear from you again. Take care. Bye-bye.